Hey, John here. Let's talk about polymorphic data types. Polymorphic, right? There's a $2 word. What does it mean? Well, it means poly means, multiple or plurality of. And morphic means the shape or the embodiment or, the way it is, right? What it is. Its form, okay? So this means many forms, all right? And what does that mean? Okay, so let's review where we left off in the last video. This is essentially the same thing. I made a couple of minor changes, so let's look at these classes. I have a class called foo, which is just an arbitrary class. I'm going to use this as a base class to demonstrate what we're doing here. So what do we got in here? A couple of constructors with different signatures. And we've got a destructor. We've got a couple of methods in here, F1, F2, and F3. Everything prints something out, so we know that they got called. We got some the get and set routines and accessor and mutator kind of thing. We've got a couple of subclasses, right? We have a bar class, which is a child of foo. It has a constructor, destructor, and it overrides F3 with its own version. We have a Baz class, which is also a child of foo, a couple of private members, a constructor, destructor, everything prints itself out. And it too has an F3 function that overrides the one in foo. We have this func object here, not an object, I should say, a func method, a function, right? It takes a pointer to a foo object and it calls F3 on that foo object, all right? Our main routine, we create a foo, a bar, and a baz, and we pass each one of them to the func object. Using a pointer, we say, hey, here's a foo. Why can we do that, right? Well, every one of these is a foo in one way or another. This is a foo, literally. This is a subclass of foo. And baz is also a subclass of foo. Therefore, all three of these actually is a form of a foo. And I can then pass it to this function up here, and then it can call F3 on whatever object has been passed, okay? And when we do this, we print out a little row of asterisks and say, here's the foo one, here's the bar one, here's the baz one. And again, this, I think, was the last demo in the previous lecture. Let's make sure everything's compiled. And run this. What do we have happen? We create the three objects. Here we are creating a foo with the default constructor. Here we are creating a bar with the default constructor, which in turn creates its parent. It passes up into its parent an integer that it uses to construct the parent portion of bar. We talked about that in the last lecture. And here is the baz getting created along with its parent object. Now we print out, hi, I'm going to pass a foo to my func program now, or my func function, and it will call F3 inside that function. So that makes perfect sense. We pass a pointer to a bar object, and when func runs and calls F3, it invokes the one that's in the foo definition, not the one in the bar, okay? Same thing happens in baz. We then destruct all these objects, all right? So let's review what's going on in the source here. We pass a pointer to a foo, a pointer to a bar, and a pointer to a baz. No matter what we pass up into func always calls the F3 that is in the base class, or more specifically, that is in this foo class right here. And the reason we see this happening is because this call here is made using what we call static binding, all right? Static binding. This is because when we defined F3 inside foo, up here, we defined it as a regular old method. All regular methods, every method we've talked about so far in this course, we've defined and invoked them as if they were used for statically bound calls, all right? So there's a new piece of terminology for you. Static binding. Now, that's in contrast to what, right? Well, we define that as static because when we move forward, we're going to create another type of binding called dynamic. Sometimes you hear this called runtime binding or late binding, okay, or dynamic binding. Let's go to poly 2 and look at that. Now, the way this works, now there's no difference between these two programs other than the comment that I just added, right? Let's do a diff and show that explicitly. Here's all the differences minus white space between these two files. Well, what have we got? The left arrow over here says that in poly 1, the first argument to diff, I have a line that looks like this, and that same line in poly 2 has the word virtual in front of it. Okay? So I added the word virtual, in other words. What happened to this line over here, the F3? Well, I added the word virtual in front of F3 as well. I threw in a comment here. There's some comments here and more comments. The only difference between these two files is I added the word virtual in front of the destructor, and I add the word virtual in front of F3. All right? Let's make sure everything's compiled, and let's run poly 2. So what happens here? What's the difference between poly 1 and poly 2 when we add virtual to it? These are constructed in the same way, and it said, hey, I'm going to pass foo to that func routine, and he's going to print out foo F3. Okay, no problem. Then when he passes the bar object to the func, notice it's now calling the bar version of F3. When he passes a baz, it calls the baz version of F3. And the destructors do the same thing as they did before as well. So let's take another look at this code. What's going on here? We'll talk about the virtual destructor a little bit later. Anytime you add virtual to any method in a class, just add it to the destructor. Okay, so what happened when I said virtual on this F3? I changed from dynamic binding, or from static binding rather, to dynamic binding. In dynamic binding, you'll see all these other words to describe it, like virtual dispatch, right? What that means is whenever I call F3 on an object that is a foo or is a subclass of foo, then what happens is it calls and it uses the most derived version of F3. All right, as you saw in our func in poly 1, because I didn't change the code between poly 1 and this is poly 2 down here. You can see this is poly 2. We left this alone. So func does not know that this pointer is not really pointing at a foo. It's either pointing at a foo or a subclass of foo. It doesn't know when it's pointing to a subclass or not. It just simply calls this F3. But because F3 was declared as virtual in foo, at runtime, this is no longer bound to the foo version of F3. It's dynamically bound to whatever F3 is defined for the object that's passed in, all right? And you saw the difference. With static binding, it always called the one in foo because P is a pointer to foo. Done. If it's virtual, if F3 is a virtual function, it will call the most derived one. So let's go ahead and comment one of these out so that I can make sure that you understand what I mean by the most derived one. If, for example, baz does not have an F3 that overrides the one in foo, all right? I just removed it by commenting it out. What's going to happen? It still compiles, and it still runs. What's going to do? Well, it makes sense that it will use the one in foo, because there isn't an overridden one, all right? So that's what I mean when I say the most derived version, right? Because remember, baz is a subclass of foo. There could be another class that's a subclass of baz. It could be an X that's a subclass of baz, and it could have an F3 defined in there to override it as well. And in which case, foo will say, hey, I got an F3, but do I want to invoke one in Baz? Well, he doesn't have one. Yeah, but if I had an X subclass of Baz that did have an F3 in there, I would then move down and say, hey, does X have one? And so on. If, of course, I was to pass in that scenario an X object to this guy here, right? So this calls the most derived version that exists in the lineage of whatever's passed in there. All right, so let's go ahead and put a 1 back in here. Where else are we at here? If you want to call the version in the parent, okay, a little comment in here. Look, it's very common when you have a virtual class in a base class and you override it in a subclass. And remember, this is the Baz class right here, right? Right there. Okay, Baz, subclass of foo. He provides F3 to override the virtual function that's defined in foo. If I want to, I can also go ahead and reach up into foo and say, yeah, I have my overridden thing to do some extra stuff here. But when I'm done with that, I also want to go ahead and execute the F3 that's in foo. This is how I can still create a statically bound call, if I want to the F3 that's in the class of foo, and tell it to do it anyway without using the virtual dispatch. So if we compile this version, you'll notice now Baz is doing some more stuff in here. When Baz runs its overridden function, he also prints out these two things, and because I added the call to foo F3 in there, you can see it reaches up into foo and calls it up there inside foo anyway. So you can go ahead and chain these things around and do whatever you want. Now be careful, don't do this, right? Because obviously this is a recursive call that will run endlessly, right? It'll compile, and it'll go like this until I run out of memory. This machine actually has a huge amount of memory, so it might take a little while to fill up and die, but there's no reason to do that. As you could see, it ran in an endless loop. Okay, so make sure you got your wits about you when you decide to do this, especially if you've got a class that has a lineage of like 18 levels, some of which have overrides and some don't. Be careful which one you call, which ancestor you use in here, to make sure that it doesn't end up calling itself, even indirectly, through the virtual dispatch table. All right, so now what's going on here? Let's look at the next one, poly 3. So in this version, let's look at what's up with this virtual destructor up here. You know, why do we have to do this? All right, let's go back down to the main. Now that I've touched poly 2, it might be a messy diff, but let's look and see for sure what's the difference between these two files, poly 2 versus poly 3. All this is in the main program. So you can see I added the if 0 and the if 1. This accomplishes nothing, right? I added that in poly 2 to temporarily comment out the F3 method, but then I put it back in. So that's why these are different, but that's innocuous. It means nothing. I deleted the func that's in poly 2, and I changed main to just have a whole lot of calls and pointers and stuff like that. So the real difference in here is what happens in main. Everything above main is the same. So let's focus on this. Given the same situation we had with poly 2, what happens if we use pointers instead of, you know, the instances that we had in the previous example? Well, when you call new and you call delete, all right, something interesting starts to happen in the area of your destructors. So let's just compile it the way it is first. I submit this will make no difference. And of course, there's no difference at all. Remember, Baz, I commented the call to the foo version, the statically bound calls back to the normal again. So what do? We create three things. So what? We use new instead of creating them on the stack. We call the F3 method in all three cases, and then we clean up. Now look what's happening here. In all three of these new statements, when I create a new foo, a new bar, and a new baz, I create a pointer to a foo in each case. The pointer to its base class is where I store these new addresses, okay? So here's what gets interesting. When I call p foo right arrow f3 like this, it's doing the exact same thing it did when I passed the pointer to the subroutine and so on, because this object here is of type foo pointer. This is not a bar pointer. It really is a foo pointer. As far as the compiler is concerned, this thing is a foo. Okay, so what? We get it. All right. What happens down here? If I delete a foo object, how does this one here in foo2, remember, is pointing at a bar? How does this delete clean up both the parent foo object and the bar object? The answer is, without this virtual destructor in here, it won't. Well, let's leave it in here and comment it out so I don't forget. Actually, the compiler won't let me forget. So the only change I'm making right now is I'm going to say this destructor is no longer virtual. Let's compile this program. Now, if you have the error wall level turned on and so on, you will get a warning in here. That'll be converted to an error because of this, okay? Deleting an object of a polymorphic class of type foo with a non-virtual destructor might cause undefined behavior. And the reason is plain and simple. If he doesn't call the destructor inside the derived type, you could have a problem. So it turns out this first one here is perfectly fine. Even though it gives me a warning, this foo pointer really does point to a foo. And when I delete it, it really will delete the foo and we're done and we're fine. But if I delete pfoo2 over here, it's really pointing at a bar. I need to not only delete the foo, I need to delete the bar. Okay, if we run this code right now, actually we can't because it's in there. Right now it won't let me go. If we shut off the warnings, I suppose, this is like it says, it's undefined, it's compiler dependent. It might be very interesting to see how bad this gets. Again, never do a call an audible in a lecture, so it might have created a poly 3. Okay, good. Right? That's what we created here. Let's see what happens. When the destructors are called, notice the only thing that happens is I've destructed the foo. When we did poly 2, notice that when I delete a foo down here, I delete the foo. When I delete a bar, I have to delete the bar and the foo. When I delete a baz, I got to delete the baz and the foo. We talked about this in the last lecture. If you do not have the destructor defined or declared as virtual, then what happens, it doesn't know that it needs to go and delete this subtype stuff. This will be absolutely disastrous if the subclass, in this case, these are simple. They just have some atomic basic native data types in here. But what if I have a dynamic thing in here, right? And it gets, pointing to a giant thing that I have to go in here and delete, all right? No one's going to delete it. This is going to leak memory in that case. We already talked about this when we talked about, these dynamic classes that have these, buffer areas, like your linked list class and your stack and stuff like that. If it turns out that your stack is a subclass of, like a foo, and foo does not have a virtual destructor, then you really can't delete in this case, this bar object or whatever a subclass is of foo, because the destructor will never go and destruct the derived type. This is a really big deal, and it can cause no end of problems, all right? Like I said, you can do this, but it's generally never what you want, which is why it warns you. It should probably just be an outright error. But like I said, there are some very specific optimizations that you can do. Like in the case we're dealing with right now, this will function okay because ultimately this class will have its data deleted. Okay, and there's no pointers in here that point to these dynamically allocated things in the heap. So, this would get cleaned up in this one example. And, like I said, because having virtual functions is a slight performance penalty, right? This dynamic dispatch takes some time. You could have a very specific situation where performance is hindered in some way, and you would not want to have a virtual dispatch on a destructor in some case, all right? But that will be very much not the norm, okay? Don't do it, all right? Okay, so you've been warned about that. What's going on in Poly 4 now? We've got a notion of, this is what an abstract class really is, okay? We have a notion of pure virtual, all right? So let's look and see what happens here. Let's do another one of these diffs. The B and W say ignore white space changes. So if I put a blank line or something like that in there, don't tell me about it. All right, so here's all the differences between Poly 3 and Poly 4. The left arrow shows, hey, you put that in Poly 3 and it's not in Poly 4. This is the little commented out foo that we left behind when playing around with the virtual destructor. Note that this can call F3. This is a call we'll look in a minute in F2. We've got an F3 in the Poly 3 that is not in Poly 4. See this? We changed F3 to what we call pure virtual. We'll go back and look at this in the context of the program. I deleted some comments. We commented out, yeah, and this stuff is in the main. So the only difference between Poly 3 and Poly 4, as far as we're concerned, is this mystery thing here. I'll show you in a minute. And I replaced F3 in the base class with this funky thing. So let's look now at Poly 4. We're back to this again. I added this call right here. There's nothing wrong with F2 inside foo calling F3. I mean, we called set J and get J. You can easily call anytime you want any other method that is in scope, right? This guy calling F3, of course, is going to be calling his virtual F3, which is kind of interesting. We'll see about what's going on there in a minute. If I don't put a F3 in here and instead I just say equals 0, it changes F3 from having a definition to only a declaration. This thing here makes it what we call a pure virtual function, and this, it being present in a class, makes that class what we call a pure, or rather an abstract class. A pure virtual function makes its class an abstract class. And the word abstract is because I can no longer create a foo. I can't say new foo anymore. We go down to the main routine, which as we just saw in the diff, the only difference in this program, algorithmically speaking, is the addition of this and the changing of this to a 0. If we come down here, I can no longer do this. All right, let's go ahead and compile this and I'll show you what happens. It's because foo is incomplete. We've said, hey, I want an F3, but I'm not going to give you one, right? That pure virtual function is going to cause the compiler to say, hey, this new expression is of abstract class type. Foo is no longer allowed. Simply because this virtual function is pure, all right? It's pure virtual. You can't do that. So don't do it. And we'll see why we want to do this stuff in a minute. If I don't create a foo one, I can't call it or delete it either. Let's go ahead and run it like this now. We see it goes, lots of things happen. Let's go back to the main. I just wanted to make sure it worked after poking around at it. Okay, so what's it going to do? It's going to create a bar and a baz. It's going to store them in foo function pointers. So when these calls are made, again, it's calling F3 on the foo object, and it's using a dynamic dispatch. So it has to call, the most derived version. We talked about that a minute ago. So here's the one on the bar, here's the one on the baz, here's the bar F2, and the baz F2. All right, then we delete the two objects that we've created. And again, when we delete them, what we're deleting is a pointer to the base class. So the base class has to have a virtual destructor, okay? So what are we doing here? Let's clear this, give us some space. All right. We ran poly4. We see it creating a bar and its parent class. We see a baz and its parent. When we call the F3 on bar, of course, it gives us F3. Even though we have a pointer to a base class, or baz rather does the same thing. When we call F2 in the bar version, when the pointer is pointing at what is a bar, it calls F2 in the base class because there isn't A, it's not overridden in bar, and B, even if it was, F2 is not a virtual function, so that would get called in the base class no matter what. And because F2 calls F3 and F3 is a virtual function, whether it's pure or not, it would call the most derived type. Okay, same thing in the baz down here. And now this is where virtual functions truly show their power. Okay, in your next assignment, we're going to be creating these shape objects and things like that. This is a very classic example. When you create an object like a foo, this might represent, say, a shape, and then you'd have a subclass that's a circle or a square or a rhombus or whatever you're going to do, okay? What happens is, the classic example is to, hey, ask, what is the area of this shape? Calculate the area. Well, a shape object might have things like its centroid location on a coordinate graph, but it has no idea how many sides or how many vertices it might have or how to calculate the area. So when you say, hey, I want you to calculate the area, we might create a pure virtual function like this in there that says calculate area. Then you'd create a subclass called, circle or triangle or whatever. And in those subclasses, you would provide what we call a concrete implementation of that pure virtual function, okay? You could also include virtual functions that are not pure. If I made this thing a regular old virtual function, that's fine too, right? This will compile. It'll probably do the exact same thing because these guys don't override F2. Let's not muddy the waters too much. Put that back the way it was. There's just no reason you can't mix and match these, is my point, all right? So this is what then happens when you say, hey, I want to write a library of functions that know how to deal with some shape object. And no matter what the shape is, any code in here in the shape object that knows how to deal with a shape object can call its other accessors and mutators, can relocate the center of the location in a coordinate graph, like I said before. It can do all that without caring what type it actually is. And you can provide all these functions up here like these guys that can deal with all that. All this can be then inherited by your circle and your triangle and so on. And it might actually be, for whatever reason, that some of these inherited functions need to know, like this guy does here, might need to know how to call a routine that is dependent on the concrete type, right? The most derived type of shape in order to do some sort of mathematical operation. Like, for example, if this thing needed to know the area in addition to things that it already knows about shapes in general, it can then kind of reach out and say, I don't know what my subclass types are going to be tomorrow, but whatever it is, I need to know the area so that it then can use its virtual dispatch, even if it's a pure virtual function, and get a value. If this thing returns a floating point number that is the area, for example, this guy here can reach up there and get the area, not knowing how it was done, and then make use of that in some other math. All right, so this is the minimum introduction and bare essence of what it means to create virtual functions. It is this dispatch, this virtual dispatch that takes place, whether it's pure or not, that causes functions to be invoking the most derived, overridden variant, okay, in subclasses that give you a lot of very powerful tools when you mix it with the rest of C++ gives you to offer, all right? So thanks for watching. I'll see you on the internet. Bye.